Recording, and I guess I'll just start right now and wait for more people to join. So, my name is Evan, uh, and this is Summations Mini-course Week 4, Advanced Strategies. So, who am I? As I've said before, I'm incoming sophomore. I'm in the class of 2024. I go to high technology high school, and okay. I guess that's it. So today, Justin and Caitlin will be TAing as usual, and Bill will also be joining us today. So if you have any questions, you can just pop it into the chat, and one of them will answer it for you, or I'll check the chat occasionally to answer your questions as well. So what did we do last week? So last week we did splitting the summand. So splitting the summand is a summation technique. It's a strategy that allows us to either split our sum into two smaller sums that we can compute in an easier way, or it allows us to implement a technique that's known as telescoping, where we split into summand into parts that are going to cancel out when we add all of the summands together. And so now what will we do today? So today we'll be learning about some advanced strategies, but what are these advanced strategies, right? So so the stuff that I'll be covering today, it's a little bit beyond AMC, okay? It's a little bit beyond AMC. For AMC, almost everything you need to know, we've already taught you in the first 3 classes, which is just like your basic arithmetic geometric sequence formulas. Those come up a lot, more often than not. Just pairing up terms, grouping up terms, simplifying the summands. That will be all you need to know for most AMC level questions. And telescoping I also comes out quite a lot in these as well. But today I'll be covering things that don't read it. Sorry, okay, Justin accidentally muted me. Great. So anyways, so the stuff I'll be teaching you is beyond a typical AMC level, but it does show up very, very frequently in AME higher level competitions. If you ever go to the Olympiad level, they come up a lot at the Olympiad level as well. So these I'll be introducing you to nested sums, products do come up considerably often, and number theory sums, combinatorial sums. So these are all, and these show up quite frequently at the AIME level, and occasionally at like the AMC Final 5, I guess. I will not be covering averages and linearity of expectation, but those are a bit of like a novelty trick, I'd say. Anyways, introduction. So so far, all of the sums that we've been teaching you about, almost all the sums, they're all algebraic sums. Okay, so algebraic sums are sums that are like your telescoping sums, your arithmetic sequences, like your run-of-the-mill summation questions, right? So most of the sums that you come across are going to just be algebra, and that's why summations, right? You typically think of them as a topic in algebra, right? But there's actually, but I tend to think of it out summations as going into three broad categories. There's algebraic summations, which we've already gone into a lot of detail, but there is also combinatorial sums and number theory sums. So those are the three types of summations that you will see in math competitions. So today I will cover a little bit about these and also a little bit about this as well. But anyways, on to our first topic, which is products. So products come up decently often on AMCs, right? Sometimes you'll see like a really easy one in the first 15 or something. And they also come up a lot at higher level competitions as well. So products are essentially, they're the same idea as summations, but instead of summing things together, as you can tell, you're just multiplying things together instead. So as we've taught you before, we already taught you the sigma notation, right? So basically you have a number at the top, some variable equals the starting number, and a function involving the placeholder variable, whatever you call it, some function involving that. And then that translates to this sum from the lower bound to upper bound. So you just sum all of these. So you might have seen like this. So if you've ever been to HMMT or something, they'll give you this notation. It sort of looks like this. I don't know. It's like a really weird. I've always found it it looks really a lot like the pi symbol, right? Like the irrational number, but this is the product notation. I don't know if it has like a Greek name like sigma, but whatever. I just call it the product notation, and it's basically an extension of the sigma notation, but instead of summing values of the function, you're just multiplying values of the function together. So once again, you have I guess you can call it the placeholder variable. You have the starting point and you have the ending point. So ending point, I guess we'll call it k n. Starting point, we'll call it k. N and k are integers, such that n is greater than or equal to k. And the placeholder I, you have a function in terms of I. And basically what this translates to, I don't know why I drew this line here, is this product of terms. So you multiply f of k plus 1, f of k plus 2, f of k plus 3, all the way to f of n. You multiply all of these terms together. So as you can see, it's a very natural extension of the notation that we use for summations. And I think this is also covered on the handout as well. So most of the time, they'll just give you they'll just write this instead. Only on like higher level competitions will they actually give you this scary looking notation. At least that's from what I recall. But anyways, that's product notation. If you see it, do not be scared. Just think of it as sigma, but for using multiplication instead. Okay. So our next, our first summation, our first product problem is from OMO. So the problem goes like this. So you define a function f of k such that f of k equals k squared plus k plus 1. So your goal is to determine the largest possible integer n such that 2015 times f of 1 squared times f of 2 squared times f of 3 squared and times f of 3 squared and all the way up to f of n squared. You want to find the largest positive integer n such that this side is equal to the square of f of 1 times f of 2 times all the way up to f of n. Okay, so this problem is a little bit it's a little bit scary, right? Because first of all, this inequality sign is a little bit annoying. It's a little bit weird. You don't see inequality signs a lot. So so what you can determine by seeing this inequality sign is usually you want to, I guess, most of the time you want to have a constant on one side. You have to have a constant on one side, and you have to show that it's less than or greater than some some expression involving n, right? And then you can go from there, some function in terms of n, something like this. Okay, so you want to create something like this, and then you can work from there. Okay, so the key idea to this problem, as with a lot of product problems, is just forcing cancellation, right? And forcing, and the way you force cancellation here is through some algebraic manipulation, through some factoring, and this problem is actually basically it's impossible to do unless you know two algebraic identities, which I'll just give to you right here because they're pretty useful to know. So the first one is n squared plus n plus 1 times n squared minus n plus 1. It equals n to the power 4 plus n to the power 2 plus 1. This identity is really useful. You should not be forgetting this identity. I've seen it come up multiple times. And the next identity is n squared minus n plus 1. It actually equals n minus 1 squared plus n minus 1 plus 1. So as you can see, there's a lot of things you can do with these two things. There's lots of cool things you can do with these. I've seen these come up in like a million problems already, but anyways, so now you can, I guess you can get a little bit of a clear idea of where we're going with this, right? Because if we plug x squared into f of k, right, you can factor that as the product of two smaller things. These two smaller things seem a little bit like what you see over here on the right side. Anyways, okay, so now we have a clear idea what we want to do. First, what we want to do is isolate the constant. First thing you want to do is isolate the constant. So you just divide this part from both sides, and then you get 2015 is greater than or equal to, let me just write it in product notation. So the product of I squared, right? So the key idea to deciphering this is to use the fact that f of I squared equals I squared plus I. It equals I squared plus I plus 1, I times I squared minus I plus 1, and this is actually equal to f of I times f of I minus 1. Okay, so now I guess you can get a little bit of a clear idea of what we're trying to do, right? So you basically have f of 1 times f of 2 times blah blah f of n, and then, on the denominator it goes f of 0, f of 1, f of 1, f of 2, so on, up to f of n and f of minus 1. So just like a telescoping sequence, these terms are going to cancel. Most of these terms in the numerator are going to cancel terms in the denominator. And I'll leave it to you to verify that all the terms cancel except for an f of 0 in the denominator, that's just 1, and an f of n in the numerator. So we're actually just left with this very simple equation, and we solve this to just get n is less than or equal to 44 if n is an integer. So 44 is our answer. And so in this problem, got a little bit crazy, but the main idea is always just to cancel terms. And the main way you can cancel terms is to have terms in the numerator of the product that are going to cancel out with identical terms that are in the denominator of the product. So it's a little bit analogous to just how like addition cancels out with subtraction, right? In the telescoping sums, like multiplication cancels out with division in case of telescoping products. Anyways, on to the next one. This is from Holiday Problems. Alright. So this one is about roots of a polynomial, which is also a setup that it's also a setup that comes up pretty frequently. So you're going to use properties of whatever polynomial you're working with to come up with some insight to figure out how to evaluate the product involving the roots of the polynomial. So you're giving x1, x2, x3, blah, blah, x22 are roots of this weird polynomial over here. So your goal is to determine this product right here. Okay? So the first thing you might be interested in doing, right? The first thing you might be interested in doing is writing this as the product of, no, you can write this as the formula of like a geometric series, right? So sequence, right? So you might write it as something like, hold on, something like this. I imagine you might write it like something like this. But the unfortunate thing is that this doesn't really work as well as we might hope, because one of the roots is one of the roots of this is -1. So things don't work out as well as you might think, because if it's -1, right, you just have 0 over 0, which is really, it doesn't work if you factor the denominator like that. So you have to so this problem is a little bit annoying, I guess, in that regard. But anyways, so how are we supposed to deal with this, right? So the way I dealt with this problem was rewrite it, right? So this part of the polynomial looks a little bit like the formula for x plus 1 cubed, right? This part. So I created a new polynomial, p of x equals x23 plus 1 minus x plus 1 3, which is actually equal to this polynomial times x. So we let x 22 equals -1. So wait, so never mind. So x 22 equals -1, and we compute this. Because that's just the reciprocal of whatever we're looking for. So, and then we also have the 23 at the end, right? Because from the x22 equals -1. So basically, we've isolated the root that we don't like, and then we're trying to we're trying to determine the product for the stuff that we do like. So now, okay, so now what are we supposed to do now? Oops, I'll just enter the waiting room. So the reason why I rewrote the polynomial like this is because we can write it as x plus 1 times this alternating sum. We can essentially rewrite it like this. Sorry. And you can, I'll leave to verify this at this part. We basically have this part, which multiplies with x plus 1 to create the x23 to the power of 1. No, x to the power of 23 plus 1. And then we have this part that corresponds with the negative x plus 1 to the power of 3. Sorry, my work is all over the place today. Anyways, so basically, we want to come up with this product over here. This product over here. And the interesting part of it is that each of these roots is also a root of the polynomial, this polynomial over here. Because by multiplying by x, right, we just added a new root, which is 0, which we're just purposely ignoring right now. But anyways, we're looking at this product over here. And this product, what we actually find is by our manipulations, we're actually looking at this. We're actually looking at the product of for each root, we multiply the root plus 1 squared over all of the different roots. So we're left with this magical equation. And the reason why we know that is because this part of the polynomial, right, is going to equal 0. So this part is going to be equal to this part. We're going to cancel out. From there, it's not that hard to just plug -1 into our original polynomial and then just square it, right? Or we plug -1 into this polynomial, and then we just square it. And so that gives us okay, so why not actually do it? So let's just compute this real quickly. Minus -121 plus -120 plus -1 squared. So this is actually what we're dealing with when we're looking at this polynomial over here. And because the reason why this is true is because we can just plug -1 into the polynomial of this using like the polynomial factorization technique, and then we divide -1 out because we do have a root of 0. Sorry, I'm being so messy today. But anyways, this all evaluates to, when we square this, it's going to evaluate to 23 squared, and then multiply 23 squared by this term over here, and then we're going to get 23 cubed, which is equal to 12,167. I definitely did not just read that off of my notes. I definitely did all the computation in my head. I did jump over all over the place, but basically what we did was we rewrote our given polynomial in a form that was a little bit easier to work with, and then we just and then this new polynomial is a multiple of the old polynomial because we just multiplied it by x, right? So then we just evaluated this over, wait, sorry, I had to take the reciprocal of everything. But anyways, sorry. But anyways, we took the reciprocal of what we wanted. So then we just manipulated the polynomial, manipulated in a way so that we just could represent it as -1 plugged into the polynomial, and then just squared that. And yeah, our final answer was 1 over 23 cubed. Sorry about that. But anyways, on to the next topic, which is generalized summation notation, right? So generalized summation notation is basically an alternative way of writing summations, and this is usually found in like summations at like a higher level, but I've also seen it used at like the AMC level. So you should know this. So the generalized summation notation is just another way to interpret the sigma notation, right? I guess it's like an extension or something. But anyways, a lot of times you will not find a number at the top. You will not find something equals something at the bottom. What you will do is find some condition, right? This condition will be like on integers, real numbers, ordered triples of things, whatever. But it'll just be some condition, and then there'll be a function. They'll give you a function, some function on everything that satisfies the condition, and this function is going to return like some numerical answer. So this summation is just going to evaluate over everything that satisfies that condition, right? So maybe it'll make a little bit more sense if I give you an example, right? So theoretically, they can give you something really, really, really stupid, like let's say x squared minus 3x plus 2, and then the function is going to be like x plus 69 or something. But anyways, as you can see, the condition is going to be x is a root of some polynomial, right? So everything that satisfies that condition is going to be a root of the polynomial. So x is going to be either 1 or 2. And then you will just evaluate the function x plus 69 over both of these. And then you would sum them up, and then you'll get your final answer of 70 plus 71 equals 141. So I was being a little bit stupid there, but my point still holds, right? So generalized summation notation, there's always going to be a condition at the bottom of the sigma, and there's going to be a function based on everything that satisfies the condition that's under the sigma. And then the summation itself, it's going to evaluate to the sum of that function evaluated over everything that satisfies the condition that was given below the sigma. So maybe like sometimes you'll see like something that comes up a lot is like summation of everything, something like this, right? It's going to be the sum of everything in a set of numbers. This comes up pretty frequently. Another one is going to be d over n, right? F of d. So this is going to be the sum of a function evaluated over all divisors of a particular integer n. These are the two ones that I most commonly see, but you also see summations on like you're going to be seeing like stuff like x, y less than or equal to some integer like 42. So then you'll be summing up this function evaluated over all integers x and y that are between 1 and 42. So anyways, that's generalized summation notation. So just keep track of what's on the bottom and what's the function that they're asking you about. So another extension of summation notation is the idea of nested sums. So these are like the sums that are like there's like a billion sigmas. You don't, your brain is hurting, you know, you just skip to the next question, but oftentimes these are worth knowing. But nested sums are all about they're all about just treating sums as functions of variables, because technically you can, right? But anyways, how I like to think about nested sums is just in general, the conditions are going to go at the bottom of each of these sums, summation, some function in terms of everything that came before. And that, so this is going to be like some variables, some whatever, some function in terms of the variables that we're dealing with. Being very vague now. And then you'll be summing the value of this function over all these variables that satisfy the conditions that are given. And a very elementary example of this would be like, I don't know, I equals 1 to 100, 100, right? And then you would be thinking about, let's say, I times j, right? So in this case, it would be the sum of the quantity I times j evaluated over all integers in all I and all integers j that satisfy the condition of being between 1 and 100 for I, and also being between 1 and 100 for j. So you're essentially summing this quantity over multiple variables that each satisfy their own individual constraints. So that's how I like to think about nested sums, but you can also think of it as like something like this, right? So for each I, you're computing this function in terms of I, then you're just summing the value of this function up over all I from 1 to 100. But I just tend to think of it as like an extension of summation generalized summation notation, which is just summing up a function over all things that satisfy a particular condition. Hopefully that made some sense. So the next thing that I'm going to talk about is swapping order of summation. So something that comes up quite a lot in nested sum problems is some swapping order of summation. So essentially, the idea goes that this happens if you treat what's inside as a function of a. So the way that swapping summation order of summation goes is you have a nested sum, right? With, let's say, two variables. We'll just assume two variables, but it can be many more. And then you just have a function of a and b in the middle. So the idea is that instead of summing this quantity over all a that satisfy the condition, you can sum this quantity over all b that satisfy the condition, right? So you've swapped the places of a and b. You're essentially swapping the order that you sum this nested sum. So once again, so first of all, you might treat a nested sum as summing up a sum in terms of b as a function of a, and you sum that function of a over all a satisfying a particular condition. Or you can take a sum over a, right? And then you can treat it as a function of b, function of b, and then you can sum it over all b that satisfy a particular condition. So treat this as a function of a, function of b. So the idea is that you can swap the order in which you sum this particular nested summation. And then one way I like to think about it is through like one of these grid things, right? So you can think of it as, so you can think of this nested sum as, so this is going to be all a that satisfy the condition, and each of these rows is going to represent a particular sum in terms of b, right? So you just sum all the rows, that over all, so you sum the value of the stuff in each row over all rows, right? All rows, and that would be like summing this nested summation this way. But you can also sum it by looking at the columns, right? You can sum it by looking at the columns. So each of the columns is going to represent a sum in terms of a sum of a over each b, right? So you can sum this over all b, and clearly you're going to get the same result as if you summed the rows this way. It's a little bit of a vague topic, but you can essentially think of it as analogous to how you can basically like flip a rectangle on its side, and then the area of the rectangle will still stay the same, right? It's like one of those commutative property of multiplication things that they used to teach me back in elementary school. And you can also extend this essentially to summations with 3 or more variables. If you have like a function in terms of a, b, and c, then you can just swap any of these around, and then you would get the same result. You can have the order of summation in any order. So the concept is a little bit weird, and the only way you can really get good at this is through a lot of practice. But and the and so you can find lots of practice on this on like the AOPS forums. I think on like HMMT comes up pretty often there as well. But anyways, onto an example, right? Because what am I even talking about? So so in this example that I made, you're summing up the following quantity, which is this sum over here, over all I between 1 and 10,000, right? So this quantity is essentially the sum of 1 over j squared over all j from the ceiling of the square root of I, which is just the smallest integer n such that n smallest n such that n squared is greater than or equal to I. But anyways, we'll get into that later, and then you'll sum this over up to 100, right? Because the maximum value that this can attain is just 100. But anyways, the key here is to, instead of summing a quantity involving, no, instead of summing the value of a sum involving j over all I, you sum over the value of j. You sum over the value of j. So the idea is that you can take j from 1 to 100 because that's all the values that j can attain, right? And then you sum for each j, you're going to sum 1 over j squared a certain number of times. So how many times are you going to sum 1 over j squared? And the answer to that is how many integers I does j appear in the sum in, right? So the answer to that is going to be all I such that this quantity in terms of I is going to be less than or equal to j. So what the critical insight is to notice that I can range from 1 to j squared, okay? Because when anything above j squared, like j squared plus 1, the square root of this, the ceiling of the square root of this is going to be greater than j. And then for that particular value of I, 1 over j squared is not going to be summed in this nested sum over here. So I encourage you to do like a little screenshot or something, and after class you can think to yourself about why this is true if you don't see it yet, or maybe one of the TAs can explain it better than I can. But anyways, once you swap the order of summation and you've got this magical thing right here, you can notice that for each j, right, the value of this little thing here is going to be 1 because it's just 1 over j squared times how many terms are in the sum. That's just j squared terms. So the trick here was making this sum, the nested sum inside, we actually were able to make it a sum of a constant. Of course, this constant is relative because so in this sum, j squared, it's essentially treated as a constant because all terms in this nested sum are the same. But anyways, this nested sum magically evaluates to 1. So you're just summing up 1 over j equals 1 to 100. And the answer to the question is just 100. So we basically, what we did was we started off with a scary looking sum. Our goal was to rid ourselves of the ceiling, right? Because ceilings are bad to deal with. And the way we did that was by swapping the order of summations and seeing for which values of I will j appear in this sum in terms of I. And by doing that, we were able to get a nested sum that was always going to evaluate to 1 no matter the value of j. If you if you like this question, thank you, because I made it, so you can thank me for it. Anyways, all right, next question. This is from HMMT. So once again, we have two sums. You know that we're gonna swap the order of summation in some way. So for every n from 1 to infinity, you're going to compute you're going to evaluate the following sum from integer k from 1 to n minus 1. So you're going to be summing the quantity k over 2 to the power of n plus k. All right. So the first idea you should get is to split the denominator. So you want to split the denominator in general into a part that involves k and a part that involves n. So the part that involves k is going to be k over 2 to the power of k, which looks a little bit like our arithmetical geometric series, right? But don't go there yet. And we're also going to look at 1 over 2 to the power of n. So once again, we're gonna swap the order of summation. So instead of treating the problem as a sum in terms of n going from 1 to infinity, we're going to treat it as a sum in terms of k going from 1 to infinity. So the question, once again, is for a given integer k, right? Which n is going which n, right? Which n is it going to appear in this following sum? So k will appear in the original nested inner sum if n minus 1, right, is greater than or equal to k. So if n is greater than or equal to k plus 1. So that's the condition. So what you're actually doing is you're essentially evaluating this following sum essentially evaluating this. So you have so now you have two infinite sums. So now our goal is to simplify the inner sum, the new inner sum that we've created, by switching the order of summation. And this can be done a little bit easier than simplifying this sum over here. This just becomes, first of all, we move k over 2 to the power of k to the outside, because that's not involving n, right? That's why we separated this, right? So in this sum, once again, k over 2 to the power of k is going to be the same no matter which n we choose in this inner sum. So we can move it to the outside like it was a constant. But anyways, as you can probably tell, this just becomes this sum right over here. You just use the formula for a geometric series. So we just get k over 2 to the power of k times 1 over 2 to the power of k. This sum over here becomes this very easy to understand fraction in terms of k. Now we've reduced our problem to just finding, right, k over 4 to the power of k. And you can just use the arithmetical geometric series formula to just get 4 over 9. That's the answer for this problem. So once again, what we did was swap the order of summation. Instead of summing a quantity from, so instead of having the inner sum involve k, we had the inner sum involve n, and this inner sum involving n turned out to be much easier to compute because we can just isolate the constant, which was just we can just isolate the constant k over 2 over k, and the rest became an infinite geometric series, which was very easy to compute using the formulas that we've already learned. And from there, it just became an arithmetical geometric series, which we can easily simplify into 4 over 9. Okay, so that's it for. Okay, so we're gonna have to skip over a few of these combinatorial sums because I do have to get to quite a bit more. But anyways, combinatorial sums. So combinatorial sums they're usually going to involve notation called combination notation. So we call it n choose k, and it essentially stands for n factorial over n minus k factorial times k factorial. And this number is going to be equivalent to the number of ways to choose k objects from n total objects without any replacement. And when you're doing a sum involving combinations, the first thing I suggest you to do is just to try small cases. Just brute force some small cases, see if you find a pattern. Because in some problems, if you find a pattern, it most likely is going to be true. And oftentimes, if you see something in combinatorial sums, it's usually going to be true. It's usually very general. So you can just bash small cases. So addition rule and multiplication rule, right? So a lot of times you're gonna interpret combinatorial sums as an actual counting problem that you will be able to understand and compute a little bit easier. And to do that, you will use the addition principle and the multiplication principle of like adding the number of ways to do one thing plus the number of ways to do another thing, multiplying the number of ways of one thing to the number of ways to do another thing. So addition principle and multiplication principle I don't know. I think that's what it's called, but it's pretty intuitive. So I'll just skip them for now. So okay, so should I go on or okay, I'll stay. So the first, so we're in this combinatorial sum, we're summing n choose 0 squared plus n choose 1 squared plus n choose 2 squared plus blah 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 plus n choose n squared. So the way we do this is to use the identity that n choose k equals n choose n minus k, right? Which is so this is a very common combinations technique. So our sum, when we write it in this way, becomes something like this, right? So you might recognize this as Vandermon's identity, right? It was covered in the handout. So this sum is actually just going to be it's going to evaluate to 2n choose n. So I would explain why that Vandermon's identity does hold true, but it's on the handout and I am a little bit strapped for time, so I'll just move right ahead. Okay, this one is a little bit boring, so let's go to my problem, which is a little bit spicier. So, all right, so this combinatorial sum is something that I made like a while ago. I don't know. So the sum goes like this, right? So it's a triple sum. You're evaluating this quantity, L squared plus n squared plus n squared. No, L plus n factorial, I'm saying, over L factorial times n factorial times n factorial, and then times 4 to the power of n plus m plus L plus 1. Okay? So you're summing this quantity over all integers L, M, and N are going to be between less, they're going to be non-negative integers, right? So there's going to be greater than or equal to 0. So this sum is a little bit scary, but you can start by thinking about how to interpret this. So once again, when you're dealing with factorials, what I'm always going to encourage you to look for is a counting interpretation, right? You're always going to be looking for a counting interpretation. And the counting interpretation, if you're lucky enough, you might find is that this is the number of ways to choose L objects. This is the number of ways to do a pathfinding in the three-dimensional plane. Okay, so this is the number of ways to get from 0, 0, 0 to LMN by taking steps in the coordinate plane, right? So each step, right, you're going to go one step up, one step right, one step up, one step in X. Wait, instead of saying up, I should just say one step forward in X direction, one step forward in Y direction, or one step forward in z direction. So once again, so this quantity over here is the number of ways to choose a path from 0, 0, 0 to the point LMN in space, where the only steps you can take is one step forward in the x direction, adding 1 to the x coordinate, one step forward in the y direction, adding 1 to the y coordinate, or one step forward in the z dimension, which is one added to the z coordinate. So this is just 3D pathfinding. So, okay. So now you need to think about this part, right? The 4 to the 1 over 4 to the power n plus L plus 1. So when you see this, you should think about is probability. So probability is something that I did not talk about at all in the handout, but I've seen it sometimes. I've seen it sometimes in summation problems. It also comes out in expectation problems as well, summation as well. Anyways, when you see this part, you should think a little bit about probability. So once again, you should be thinking about how to interpret this as a counting problem, right? So if you're lucky enough, of course, I cannot walk through all the motivation for you because we're so short on time, but if you were lucky enough, you might consider the following problem, which I based this sum off of. So so let's say we have a frog. I just called it a frog. So like frogs starting from 0, 0, 0. Each move, right? Each move, it either stops, goes one step forward. It goes one step forward in the x direction. It goes one step forward in the y direction. It goes one step forward in the z direction. So each move, it either stops, goes one step forward in the x direction, one step forward in the y direction, and one step forward in the z direction with equal probability. So 1 over 4 probability for each, right? So the question is, what is the probability that it's going to stop at the point L, M, N for non-negative integers L, M, and N? So once again, it starts from 0, 0, 0. Each move, it either stops, it goes one step forward in the x direction, one step forward in the y direction, and one step forward in the z direction, each with equal probability. So the idea is that the probability that it gets to LMN, point LMN, and then stops there is going to exactly be the value of the term that we've had here, right? So we basically have number of ways to get there over the number of total possibilities. And then there's a 1/4 probability that it's just gonna stop there. So the key to this problem is that the frog, or whatever you want to call it, it's going to stop at some point. It's going to stop at some point LMN with non-negative integer coordinates, and it's always going to stop there. So we're summing up the probability that it ends up at each point every point that is possible. So the sum of the probabilities is actually going to be exactly 1. So this sum, this really complicated looking sum, is going to evaluate to exactly 1. And the reason why it evaluates to exactly 1 is that we're summing up the probabilities that it ends up at each option in a particular probability problem over all options, all possible options in that problem. So once we sum up all the possible probabilities, and we're actually going to get exactly 1 as our answer to this absolutely monstrous looking problem. So anyways, this is okay, so this problem is probably never gonna show up in any legit competitions, but I just found it very interesting, and just in case like a probability related sum shows up in the future, I decided to just put it here, because why not? So once again, this is just an example of how you should always be looking for a way to interpret your the problem as a combinatorial setup. And so in this case, we instead of interpreting it as a counting problem, we interpreted it as a probability problem. So anyways, hope you found that cool, because I did make that problem myself. So anyways, number theory sums. So you're going to be dealing with 3 number theory functions. So the first one is going to be phi n. So phi n is a function in terms of a positive integer n, and it goes how the number of integers relatively prime to number of positive integers relatively prime to n that are also less than or equal to n. So for example, like phi of 6 is going to be, let's say, it's going to count 1. It's not going to count 2. It's not going to count 3. It's not going to count 4. And it's going to count 5, and it's not going to count 6. So in this case, phi of 6 equals 2. So that's 5n. It shows up decently often. Divisor function d of n, number of positive divisors of an integer n. And S of n is going to be equal to the sum of the positive divisors of an integer n. So once again, d of n is going to be 4, because you're counting 1, 2, 3, 6. And S of 6 is going to equal to 12, which is just 1 plus 2 plus 3 plus 6 equals 12. So these are the 3 like big functions that you should be pretty familiar with. There are closed forms for them based on the prime factorization of those integers. Unfortunately, I can't get into them now because I'm short for time, but they are posted in the handout from what I can recall. Okay, let's do this one because it's easier. Okay, this one is another of my horrible creations. Anyways, so you're summing up the quantity 1000 over n minus d of n, where d is the number of positive divisors of n. You're summing up this quantity over all n between 1 and 999. So the key here, the first key here is going to be, so first of all, the summand, you have no idea how to simplify the summand. Can you really write this in a better form? I do not think you can write it in a better form. So the first thing you do is split the summand. You split the sum into two parts. The first part is this part involving the for function. And the second part is going to involve the divisor function. So as I've told you before, the for function is absolutely horrible. It's absolute trash. So you want to get rid of the for function as quickly as you can, right? And the way you do this is by taking a look at so you take a look at n. So you want to so the goal is to relate this to the divisor function, right? You want to relate this to the divisor function, but how are you going to relate to this to the divisor function? Well, instead of thinking about divisors of n, maybe you might have stumbled across the idea that you can think of this function as dealing with you can think of this function as dealing with multiples of n. So this is actually, this summand, you can actually think of it as the number of multiples of n from 1 to 1000. Okay? Number of multiples of n from 1 to 1000. Oops, sorry. What the heck? Sorry, I don't know, my app glitched. Anyways, number of multiples of n from 1 to 1000. That's going to be how we think about this for function from now on. So now we just move this up a little bit. Give me some room. Number of multiples of n from 1 to 1000. So for each n from 999 to 1 to 999, is we're summing up we're summing up, right? We're summing up the number of, okay, so we're summing up the number of so summing up the number of divisors. M is, I guess I'll write it, n right? You're counting the number of divisors between, counting number of numbers between 1 and 1000 that are a multiple of n. So the key here is, as I've told you before, we're gonna switch the summand. We've created a nested summand. No, we created a nested summation. So we're going to switch the order of summation. And the idea is that instead of summing over the number, instead of summing over m, right, we're going to sum over m. So we're just going to sum over m from 1 to 1000. So in how many, this is the funny part, in how many n is this going to be, is m going to be counted? And the answer to that is if n divides m. So we're actually summing over the quantity 1 over all n that divide m, right? We've swapped the order of summation, and now you can see that we've actually gotten something really funny, because this sum over here it evaluates to exactly the divisor function. We've swapped the order of summation, and we've gotten a sum that looks very much like the right side of this right side that we've been ignoring for most of the problem. So now you can see that Squareman has magically contrived this problem so that 999 of the terms are going to cancel out. So all you're left with is d of 1000, right? Because that's just the number, because that's the only integer that's left, right? The integer, the number at the top. So you just have d over 1000 as the only thing that's left when it cancels. And you can evaluate this to be, it should be 4 times 4 equals 16 if I'm correct. But anyways, cool problem, I guess. But what you've done here is first you've swapped the order, you've split the summand into two sums. You've written one of these sums purposefully as a nested summation. You've written it as a nested summation. You were able to swap the order of summation and create another nested summation, but then this other nested summation simplified to a sum that shares a lot of terms with the summation that on the right, the other summation on the right. So that caused a bunch of terms to simplify, and it caused our work to be quite easy. So 16 is our final answer for this question. Okay, this question is a little bit too difficult, but I do want to go over to exploiting symmetry as our last topic. So exploiting symmetry is probably one of my favorite summation techniques, and exploiting symmetry is always going to be about doing something with the variables. It's going to be switching the variables in some way. And if you switch the variables and the variables essentially fulfill the same tasks, right? They're all being summed from in the same range. You can switch the variable names, and what will actually happen is that you will end up with another sum that has the same result. So there's going to be, suppose you have like a function like this, f of a, b, c, then you can switch the order of these variables around as long as they're each being summed from in the same range, right? They're each being summed over the same set of numbers, right? So if we had like the starting number for B is 2, the starting number for C is like 7, we wouldn't be able to switch the variables anymore, because then there's no symmetry between A, B, and C. So symmetry is all about switching stuff, and you're going to notice that nothing is going to change, actually, which is what is a little bit interesting. So f of A, B, and C, it does not have to be a symmetrical function, but as long as this A, B, and C are summed up for the same quantities, we can switch the order of the variables, and then the sum will evaluate to the same result. So let's take a look at an example, okay? So let's take a look at this, okay? So another thing that I made. So once again, notice that A, B, and C are all going to be summed from 1 to infinity, right? They're all going to be summed in the same range. So that means that A, B, and C, they can all be interchanged, and the sum will still end up evaluating to the same exact thing. Anyways, so you're taking a look at this summand over here. right? So in the numerator, it's going to be a squared plus b squared plus 2bc plus 2ca. It's very asymmetric, this numerator. The denominator is symmetric. The denominator is symmetric with respect to all three variables because it's just a plus b plus c times a times b times c, and you take the whole thing and you square it. So the idea here is that you can switch the order of the variables, right? You can switch the order of variables in this function, and you will end up with the same sum. So let's take, so for example, if we had b plus squared plus c squared plus 2ba plus 2c, no, sorry. Yeah, so, and then over, this sum will evaluate to the same result. And so will this sum over here, okay? No, I haven't even written this sum. So this sum over here will also evaluate to the same thing. Hold on, give me more room. There we go. Okay, so all these sums, notice that we're just swapping the order of the variables here. So by just swapping the order of the variables right here, since we're all summed in the same range, we're actually going to end up with three sums that all evaluate to the same quantity. So what happens is you can add these three sums together. Compute the value of that sum, and then divide by 3 to get the value of our original sum over here. So this is a very novel trick. I don't know. So you're basically adding up 3 copies of the same thing, simplifying that, dividing by 3 to get our original thing. Okay, so when we add these 3 things up, what do we get, right? So you might have noticed that we actually get, let's write this very quickly. We get 2a squared plus 2b squared plus 2c squared plus 4ab plus 4bc plus, I cannot, okay, so 4ca, I should just squeeze that in, over the same denominator, right? Because the denominators, they're all the same, so we're lucky, right? We can just have the same denominator in each of them, not care about like adding fractions. It's much easier. So now the key to realize, now the key insight is that this numerator is going to evaluate exactly. It's going to evaluate exactly to 2 times a plus b plus c squared. Okay. So this numerator is going to factor exactly like 2 times a plus b plus c squared. So the genius part of this is that the 2 times a plus b plus c squared is going to cancel exactly with the a plus b plus c squared in the denominator. So now what we're left with is that this summand, we've simplified the summand to just become 2 over a squared times b squared times c squared. So we now simplified our very complicated looking summand to much simpler looking summand. But how do we deal with that? How do we deal with this? How do we deal with this weird thing over here, right? Well, the answer to that is that we just factor the sum, as I think I taught this in a lecture, one of the lectures before, but you can actually factor the sum as just 2 times this times this times this. And once again, by the Basel problem, which I covered in last week's class, I discussed briefly in last week's class, right? Each of these sums is going to evaluate to pi squared over 6. Pi squared over 6 here, pi squared over 6 here, pi squared over 6 here. So almost running out of room, but so our final answer is going to be 2 times pi squared over 6 cubed, and that's going to be equal to pi to the power of 6 over 108. So that's our final answer. So here, what we did was we started off with a very scary looking summation that I made, and then we swapped the order of the variables. We're able to add these three sums that we knew evaluated the same value together. Oops. And then when we added them together, and then we were able to simplify the sum. Also, I just noticed that I forgot to divide by 3. So it's actually just going to be pi squared over 6 times 324, sorry. But we added these three sums together. We were able to factor the resulting sum in terms of problems that we already knew how to do. And then we divided by 3 again to get our final answer, which is just pi to the power of 6 over 324. So this is just one example of exploiting symmetry in summation problems. Unfortunately, we're out of time, so I'll just skip the rest of the problems I had in mind and just go straight to the conclusion. So what did we do this week? So we talked about advanced strategies in summations, right? So we started off with products. We went and talked a little bit about nested sums, switching order of summation. We talked about generalized summation notation, which is just like a generalized version of the sigma notation that you're used to. We talked about NT sums, and we talked about combinatorial sums, and we touched a little bit about exploiting symmetry at the end. Okay, so what to do for next week? Do the homework, do the last homework set. The last homework set, it's a little bit hard, I'd say. It's higher than AMC level because the topics here are higher than AMC level. If you have any trouble, you can ask me for hints. You can ask me to explain. These are tricky topics, so you can ask me anytime on Discord if you have like a particular topic that you need more explanation over, or you can ask like one of my TAs who can probably explain it better than I can. And so just don't be afraid to ask if you have any questions, because these are important topics even though they're hard. And I just keep practicing summations. This is the last class, so I guess I'll recommend some contests for you that do a lot of summations. Purple Comet, if you're interested in summations, they have like a ton of telescoping summations. I checked the forum. Carnegie Mellon, HMMT, PUMAC. These are all great questions. These are all great contests to look for summation problems on. Yeah, to do. But anyways, this is the last class of the Summations Mini-course. I hope you guys had fun working on the problems that we gave you, listening to the lectures. I'm sure that you understood 0% of what I said. Anyways, thank you for attending. we appreciate like your enthusiasm, and we hope to see you in a future mini course or just another app lecture. If you have any questions, you can let me know. If not, then I'll just pause the recording.